now is go back to the pigeonhole principle. And I mentioned, pigeonhole principle is quite powerful, and sometimes you have to be a little bit creative about what are my pigeons, what are my pigeonholes, and how does a pigeon occupy a pigeonhole. But let's do one example of this type, and then I'll state the more general pigeonhole principle and prove that. So let's do one example. Suppose we have, let's say, S is a subset of N, and S is finite. The finite subset of N with the cardinality of S greater than or equal to 3. We want to prove there exists, I'll do this in symbols, X, Y, and S distinct, such that X plus Y is even. Now, I will say before I begin this, natural numbers, 1, 2, 3, 4, 5, 6, etc. 0 is not a natural number. We use pigeonhole principle. And how are we going to do this? Okay, well, the elements of S are the pigeons. What are my pigeonholes? This is where perhaps it's a little bit of creativity. My pigeonholes are this, even, comma, odd. And then we assign a pigeon to a pigeonhole based on its parity. Pigeonhole based on its parity. Okay, so you assign the even elements of S to that pigeonhole and the odd elements of S to this pigeonhole. Okay. Well, you notice, so as the cardinality of S is strictly bigger than 2, it's at least 3, so it's bigger than 2 by the pigeonhole principle. What do we have? Well, so there exists, let's say, X, Y, and S. We have 2 pigeons that are distinct, and X, Y are both even, or we have that X, Y are both odd. This is another way to say that we have this one pigeonhole, or at least one, but we have one pigeonhole that contains 2 or more pigeons, right? So it's either this pigeonhole or this pigeonhole that's guaranteed by the pigeonhole principle, and we would have these 2 different things that are in here or 2 different things that are in here, and adding, in either case, X plus Y is even. You take 2 even numbers, even integers I should say, you add them, even. You take 2 odd integers, you add them, even. Okay, so we have proved this. We found this was pigeonhole principle. Well, what I'd like to do now, and I'd like to use the whole board, so I will start back up here, is I would like to state a generalized pigeonhole principle and prove it. And this will, in fact, we will be proving the pigeonhole principle I already stated with proving this more general one. Let's suppose we have capital N pigeons. we have N pigeons that occupy, I will say, that occupy K pigeonholes. Okay, so far so good, it reads the same. Well, except instead of X and Y, I have N and K, but in any case, but here's what's different. So then, there is at least one pigeonhole containing at least the ceiling of capital N over K pigeons. Okay, now let's prove this. But by contradiction, what do we assume? We have N pigeons and K pigeonholes. We have capital N pigeons. And we have K pigeonholes. And what we're trying to assume, let me underline it, there is at least one pigeonhole containing at least this many pigeons. This is what we need to assume is not true, right? In order to get a proof by contradiction. So, okay, at least one pigeonhole containing at least N over K pigeons. What would be the negation of this? Well, it would say that every pigeonhole contains no more than this minus 1 pigeons. This is our assumptions. Okay, what is the total number of pigeons? Is no more than, what's the maximum number we can have? Well, we have K pigeonholes, and they contain all of them no more than the ceiling of N over K minus 1 pigeons each. So the most possible pigeons we can have is this product. But now, what can I say about this? This is strictly less than. Well, this ceiling of N over K, where we round up. So I can say that this number, the ceiling of N over K, it's strictly less than N over K plus 1. Because I'm rounding up, but I'm never going to jump up a whole integer. So it's strictly less than this. And then I keep the minus 1. And this is, well, you see, this is just N. So what I have, the total number of pigeons is no more than some number which is strictly less than N. And this contradicts that we have capital N pigeons. And this would be the end of the proof, okay? This is going to be a generalized pigeonhole principle example. And let's think about this. So we have 26 letters. And we want to think about the number of first, middle, and last initial like this. This is a list of length 3 or a string of length 3 over this alphabet. Now, again, something I'm also assuming is that everyone has a first, middle, and last of these residents, and that may or may not be the case, but for the purposes of this example, every resident has a first, middle, and last initial. Okay, so we can count these. We have 26 options for the first, 26 options for the second, and 26 options for the third. Is 26 cubed. Okay, so if we think about this generalized pigeonhole principle, my pigeons are Boston residents, and we know how many of them they are right there, 685,094. And my pigeonholes are this list of length 3 are these things: first, comma, middle, comma, last, initials, and now we just calculate, right? So clearly the number of pigeons is bigger than the number of pigeonholes. Well, maybe it's not clear because this is something cubed, but it is. But we don't want to just say, well, at least 2 residents have the same first, middle, last pairs. We can use this more generalized version. And so to use this, we would take the ceiling of 685,094 divided by 26 cubed. This is, I have to look because I don't have my calculator. This is 39. So I think in my calculator I got this was 38.9 something or other. So this is 39. And so this is the answer. 39. Here. 39 residents. At least 39 residents must share the same first, comma, middle, comma, last initials. Now this doesn't tell us in particular which initial pairs out of all of these that is shared, but just there's at least one such that 39 residents share that same first, middle, last combination. Example, this will be our last. How many people are needed in a group to guarantee at least 4 were born in the same month. At least 4 were born in the same month. And I don't mean the same month and year, so I will mention perhaps different years. Let's think about the pigeons and the pigeonholes. We have 12 months. Okay, the 12 months. These are our pigeonholes. And I will say the N people in the group that we're interested in making, or how many people do we need, and people, these will be our pigeons. And we want to guarantee, so we want, the smallest N, such that when you take the ceiling of N over 12, we get 4. And this would be the smallest number of people we could put in a group to guarantee that 4 of them were born in the same month. Well, here you can see how to answer this. It would just be 3 times 12. That won't work because that's 3. When you divide this by 12, you get 3, but you take 1 more. So plus 1, we get 37. So if we have a group with 37 people, we are guaranteed that 4 of them were born in the same month. Okay? This is the pigeonhole principle.